So turboprop engines, let's get in it. Gas turbine engines, you got 4 basic types. Now I've got 5 there because one kind of breaks down a little bit, but turbojet, turbofan, high bypass turbofan really is just another type of turbofan engine. Turboprop and turboshaft. So we're going to mainly be looking at turboprop for propellers class, but just a quick review of kind of what these look like. There's those 4 main types: turbojet, fan, prop, and then this is an afterburning turbojet. A turboprop and a turboshaft are basically the same thing. It's whether it's feeding a propeller or feeding a gearbox and rotors on a helicopter, or potentially powering something like a generator or something like that. But turbojet engines look something like this. Air enters at the front, and the reason we do this is at the core, every one of the other engine types, a turboprop, a turboshaft, a turbofan, is going to have essentially a turbojet at the core driving it. So in a turbojet engine, all the air gets pulled in. It goes through a compressor stage. So you've seen the suck, squeeze, bang, blow, with a bunch of money going in right here in the form of fuel. Okay, you got to have money. I just got a bill for Duncan for jet fuel for one of these. But anyways, inlet, compressor, then we go into combustion chamber and we go through the turbines and out the exhaust. Okay? So just a quick review of our turbojets that we saw. These were the first type that was manufactured. And then since then, the other types, turbofan, turboprop, turboshaft, have been developed based on this core. And so in this case, all the inlet air is used for the combustion process and for cooling. Okay, internal cooling. These are internally cooled. So the air that goes through the engine also provides the cooling. In fact, the majority of air, roughly 80% of the air going through the engine, is going to be used for cooling. Only about 20% mixes with the fuel and is ignited, as part of that stoichiometric ratio of fuel to air that supports combustion. But it all travels, all that air is traveling through the core of the engine. Okay? Even the air that's not being burned, not supporting combustion directly, is going to pass through the combustion, through or around the combustion chamber, and then it's going to pass through the turbine area and out the exhaust. And it's going to be accelerated out the back. And so these work by accelerating air from the inlet to the exhaust. Okay? And even a turboprop has a certain amount of jet thrust from the core. Okay? So we take, what is thrust? At its very basic term, what is thrust? Thrust is what? A what? A force, right? Thrust is a force. Okay? So thrust is a force. And what's a force equal to? Mass times acceleration. Right? F equals ma. Mass is the air we're moving, a bunch of air we're moving. The acceleration is how much faster is it traveling back here at the exhaust compared to the inlet, right? And acceleration is a difference in velocity. Okay, so the engine is speeding this up. And turboprops basically work in a similar fashion. We're just going to accelerate the air slightly different. But in this case, all the air is going to travel through, and it's going to be moving faster when it comes out the exhaust than when it comes in. And that acceleration times the mass of the air is going to push the engine forward. And hopefully that engine's connected to an airplane and pushes the airplane forward. Okay. Or, pushes on a test stand. So the first one of these was the de Havilland Comet. Had 4 engines. They developed about 5,000 pounds of thrust each. Today, 5,000 pounds of thrust is a turboprop. Most turboprops large turboprops can generate that. Okay, I don't think, there's not too many turbojet or turbofan that generate that little amount of thrust. Okay, fairly small. Okay. So then another iteration of this is a turbofan engine. And in this case, it's basically the same basic component. So from about this point here back, or from, besides the area in green at the front on this one below, but the gray, red, pink, down here, that's still a turbojet core. It's still essentially a core. But now we're spinning a big fan at the front. And so in this case, the air coming in the inlet, a portion of it's going to travel through this core. A portion of it's going to travel around the outside here. That's accelerated by this big fan. Okay? So half or more of the air is going to pass around the outside of the engine. The early versions of these, it was about a 50-50 ratio. About half passed through the core, about half passed through what's called the bypass, the fan bypass. And that you have essentially a larger amount of air that has a small acceleration. You have a smaller amount of air going through the middle that's got a big acceleration, and altogether they create thrust in the form of a force moving, acceleration. And these are more efficient than turbojets, and they're quieter because we don't have to accelerate the air as much. The majority of noise comes from turbulence. The more you accelerate air, the more turbulence is in it, the louder the engine's going to be. And so some of these, an example of this, Pratt Whitney JT8, this is what's on the 727. It was on the early variants of the 737. These had a 1-to-1 ratio. So they had roughly the same amount of air going through the core as around the outside. Today, we have what are called high bypass and even ultra high bypass. And these are up to 80% of the thrust comes from that fan. And the reason we're going in this order is essentially these fans getting bigger kind of act like a propeller, just accelerating air. And so when we get into a turboprop, it's not much different from a turbo fan. It's just the propeller's even bigger, right? It's essentially a giant bypass ratio with a small amount of air going through the core. But here, they can be, 5-to-1 is considered high bypass ratio. The Boeing 777 shown here, which is the highest thrust engine in production. The GE90 it's been replaced by the Gen X. I don't know, there's one that's a little higher now. But 115,000 pounds of thrust each per engine, right? So we went from that Comet that had the engines that had 5,000 pounds of thrust each. Now we're on this size that has 115,000 pounds of thrust each side. So 230,000 pounds of thrust total. The Comet had 4 times 5, 20,000 pounds of thrust. Okay. That's a 9-to-1 ratio. Some of your newest ultra high bypass turbofans are pushing 12-to-1 ratio of the mass of the air moving around the outside of the engine versus the inside. And what that takes us to is our turboprop is essentially an ultra high bypass engine. Because we have this massive prop that's moving air. Now, it's not going to accelerate as fast as the fan in a turbofan will, but we're putting a smaller acceleration into a much larger mass of air. Okay? So it's a gas turbine engine. It's still, you look at this to the right of the prop here, it still looks like a turbojet core, right? Nothing looks too much different there. It's still got a compressor section, it's got a burner section, it's got turbines in the back. But now what we do is we take rotational energy, and instead of just trying to accelerate air inside the engine, we use a turbine, or more than one turbine, but one or more turbines, to extract energy from those exhaust gases. And we turn a gearbox that turns a propeller. Because these are spinning much too fast. If we hooked a propeller directly up to one of these, first of all, it would put too much resistance on the turbine. The turbine would overtemp. But the other part of it, if it was actually able to get to speed, the prop, probably the outer half or more of the prop blades go supersonic. So we have to slow that rotation down, but we get a lot more power out of it. We get that energy is now in the form of torque and can be converted to thrust using the propeller, and keeping those tips, those blade tips, just below the speed of sound. We don't want them to go supersonic. But in this case, we extract roughly 90% of the exhaust gas energy to spin the propeller. So there is still a small amount, about 10% of the energy coming out the exhaust, and that can add to thrust. In fact, if you look at the type certificate data sheet for aircraft that are turboprop, it will list how much thrust comes from the propeller, and it will list how much thrust comes from the exhaust. And I've seen it, I'm trying to remember the Saabs I worked on, I want to say it was about 60 or 80 pounds of thrust from the exhaust, and then, several thousand pounds of thrust from the propeller, right? It's negligible, but it's still there. They take it into, yeah, you may as well use it. I think the smallest, I saw one where it was like you got 15 pounds of thrust out of the engine. I can't remember what airplane that was, but they still count that extra 15 pounds of jet thrust. And we use that to get that propeller spinning and convert it into thrust. So turboshaft works roughly the same as a turboprop, except now we're going to take that energy, that power output, rotational energy, we're going to drive a gearbox, and we're going to drive a really, really big propeller that's mounted up top, above the head, and drive a rotor. These can also be used to drive things like generators and serve as an auxiliary power unit. In fact, this engine right here is an Allison 250. It's installed in helicopters. There's also derivatives of it that are used as APUs on larger aircraft. It's made by Rolls. It was originally made by Allison. Now it's a Rolls-Royce, and they've changed the name of it, but it's the same basic core. You have a compressor, and this one kind of flips the air around. Compressor air comes out into this, goes down these tubes. Here's the combustion chamber, and then the air comes forward. There's a turbine, and then out the exhaust here, left and right. And then an angle. Okay. But we're extracting, and then the output, there's a output shaft down here on the bottom of the gearbox. The gearbox is kind of in the middle on this one. And so the gearbox you'll see is typically mounted right behind the propeller. The propeller is mounted right to the gearbox in most cases. Sometimes it's integral to the engine, like we have here. I believe there is a turboprop version of this. I can't remember what airplane it's on, but there are other engines that can be that way. They often use what do they call it? A planetary gear type system to make the gear reduction. And so, which allows a large amount, it's a very strong gearing system that it transfers that force through multiple gears and allows a large gear ratio. You need a fairly high gear ratio. And in this case, you can see a shaft coming in. This is our our planetary gear system up here in the front. It also has an accessory gearbox here with things like devices to measure propeller speed. This is where your propeller governor would be attached, okay, to this gearbox. This is separate from an accessory gearbox that would drive things like a generator or where the starter would be attached. So the engine core would often have an accessory gearbox. And the accessory gearbox, like I said, that's going to be the starter, the generator, the oil pumps, fuel control. If you have hydraulic pumps for the aircraft, those would be driven off of the accessory gearbox. And then you have a propeller gearbox, which primary job drives the propeller, but it's also going to drive your prop governor. It's going to drive your overspeed governor. It's going to drive sometimes they have a separate oil pump in that area. The Saab 340s I worked on, they had a GE, what's called CT7. It was kind of set up like this, where you had the shaft, you had a kind of a core engine back and then the shaft coming forward. That actually had two oil filters. It had an oil filter for the main engine. It had an oil filter for the prop gearbox. It had an oil pump for the main engine. It had a prop gearbox oil pump. So you had two oils you had to check on the engine. Okay. The PT6 that's on like our King Air, that has a single oil system for the prop gearbox and the engine gearbox, and the accessory gearbox and the main engine. So designers, companies can make them both ways. And like I said, they can do multiple ones. The engines that were in the Saab, the CT7, was a turboprop, but they made a turbo shaft version of it as well that was in the Black Hawk helicopter. So they can adapt these multiple ways. There are two main types of turboprop engines, and it has to deal with how power is taken off the engine and transmitted to the propeller. And they're called a fixed turbine and a free turbine system. So in fixed turbine systems, the compressor and the turbine form something called the gas generator. Okay, and both engines, the compressor plus turbine is called the gas generator. The whole point of these turbine engines, the core of this engine, is to generate combustion gases that that power can be extracted from to turn the propeller. And then the prop gearbox is driven directly off of the gas generator, the compressor and turbine spool here. The other type of free turbine is our gas generator compressor. Our gas generator is made up of a compressor and a turbine. That's one spool. And then the propeller, through a gearbox, is not connected to that gas generator, but rather it has its own turbine that's designed to extract energy from the exhaust gas before it leaves the engine. So if we look at them a little closer, this is our fixed turbine. So you can see here, again, the core, just like any other turbine engine. This turbine back here exists to drive the compressor. It's also going to spin the shaft, powering the gearbox and turning our propeller. And then that propeller is going to accelerate a large mass of air to give us thrust. Okay. In a free turbine or free power, it's also known, you'll hear it called a free turbine or a free power turbine turboprop. We have that core, as I talked about, and these are two different versions. This is kind of like what the PT6 is like that's on the King Air, where the inlet is at the back and the exhaust is at the front. That's why the King Air's got those kind of two exhaust ducts coming out on the side. That's one configuration. And the advantage to that is we have our inlet at the back. Air goes through a compressor. Here's our combustion area. Goes through a turbine. Now this first set of turbine stages, it shows two stages here. You can see drives, it exists purely to drive the compressor, to create that air that's needed to support combustion and cool the core. And then the air that comes off of that, which is still the majority of the energy, then goes through this green turbine disc here, which it exists solely to power the propeller. Powers the prop gearbox, powers the propeller. So when you walk up to one of these, if you go up to the King Air, you move the propeller, you look in the inlet, you will not see the compressor turning at all. Compared to this style, which is, we have one of these over in the turbines lab called the TFE 331, Garrett or Allied Signal TFE 331. When you turn the propeller on that, you can see the compressor at the inlet, you can see that rotating. Okay? Both of them, you can see the turbine rotating if you look in the exhaust, because it's the last turbine stage that makes up the free power turbine. So here, if you go spin that propeller, the only thing you'll see moving would be the turbine and the exhaust, but you wouldn't see any movement on the compressor side. Okay. Another configuration is what's called a coaxial configuration, which isn't that important. Don't worry about remembering that. But in this case, inlet's at the front, exhaust is at the back, so it's kind of set up like a typical engine. But you have two shafts, one inside the other. So your compressor, which is driven by what they call the core turbine or the gas generator turbine, is an outer tube. And then running through the middle of that is a shaft that goes from the power turbine or free power turbine up to the gearbox in the front. But they are not connected in any way. So again, if you go up and you move this propeller, you turn it, if you were looking in the inlet, you would not see the compressor move. If you look in the exhaust, you would be able to see the power turbine move. Okay. When you're starting these, what that means is on a fixed turbine, the gas generator here, which does drive the propeller, it also, we've got the prop gearbox, it's also going to have an accessory gearbox here, and the starter would connect to it. So when we engage the starter, what happens to the propeller? What does the propeller start doing immediately? It starts spinning. And that propeller is going to put a certain amount of resistance on this spinning, right? So which way do you think you want your propeller blades during the starting process? What direction do you want your prop blades? You want them in low pitch, fine pitch position. Okay. So that's another way to tell these apart, is if a fixed turbine turboprop engine is sitting there and it's turned off, the blades should be in the fine pitch position. Okay. And that's where those locks come into play. We'll talk about them a little bit more as we look at some of the different engines. But there are fine pitch locks that are designed to drive it into that low pitch position, because the prop is going to want to go to, they're designed to fail to feather normally. Right? In flight, if you have a failure, you want them to go to feather, but during a normal shutdown, you do not want it to feather. We'll look at that. And so these typically are going to be sitting in fine pitch position. They also tend to have a pump or some way to be able to get them to fine, or to get them back to fine if for some reason they shut down in feather. Okay, they still often call it a feathering pump, and often they can drive it to feather or to fine pitch. You can actually drive it both directions in many cases. What about our free power turboprop? When we hit the starter on here, what happens to the propeller? Doesn't spin initially. Okay, do you think it starts to spin at all? It'll typically start to spin very slowly, because as the starter rotates the compressor, you're going to start getting airflow through here. And so you will see it spin. However, it doesn't have to spin. And when I worked on these, when I worked on planes that had these, which was the CT7 on the Saab 340, the Pratt & Whitney, I am drawing a blank. The Embraer 120s I worked on were free power turbine. And then the King Air is the other turboprop that I worked on. Those are all free power turbine. You can actually hold the prop blades while you engage the starter. And there were times we would do that. If we were doing a compressor wash, we would spool up the starter and we'd spray water through the engine to wash it. Yes, you do that with turbine engines. We would hold the prop blades. They would not try to, I mean, there was a little bit, but not much force on them. Now, we're not lighting the engine off. You don't want to sit there and try to hold it while the engine lights off, but you could hold it. And we'll do that when we do tests on the King Air. There are times where we hold the prop blade while we spool it up. But we make sure the igniters are shut off. We make sure that fuel, the fuel is cut off to the engine, because you don't want it to ignite when you do that. The Saab 340 I worked on had an option where the airplane didn't have an APU. It was DC powered. It used DC starter generators. It did not have an APU. And at one point, they offered an option where you could put essentially a giant disc brake behind the right-hand propeller. And when the engine was shut down, you could engage that brake like a parking brake, start the engine, and have the core running without the prop spinning, and it essentially treated it as an APU. But if that brake failed, it went from 0 to full idle RPM like that. They only put it on the A model. There was an A model, a B model, a B+. They realized it was probably a bit of a liability nightmare, and they stopped offering it as an option. The only airline I know of that took it was American Eagle. So, you can, in many cases, these can be held stationary while the engine's running. It'll cause it to run hotter. You would only run it, and by held stationary, I mean like a prop brake is holding it stationary, or you hold it stationary while you do a comp wash. If you try to hold one of these when you engage the starter, it could potentially lift you up off the floor. There's a big gear ratio between that electric motor and the prop. So you want to be careful, know what you're working on. If you've never worked on it before, don't just go up and be like, oh, I'll hold the prop while we test the starter and get launched across the hangar. Okay. So, because you will go somewhere. That electric motor is not going to care that you're holding onto the propeller. You're just a squishy human. Okay. So with any of these, though, we measure the power output in horsepower. Okay, even though do turbine engines inherently put out horsepower? Typically they don't. They do a thrust of force. They do pounds of force. So we have to convert that to horsepower. And the way we do it is using this. So horsepower is determined as what's called shaft horse. So there's a couple different ratings we can look at with these. The first one is shaft horsepower. How much power are we putting into the propeller? Putting through that output shaft. And what we do is we take our we have to know our propeller RPM, So it's at a given RPM. You know, the faster it's turning, the higher the RPM, the more power it's going to be putting out. So propeller RPM times torque. And torque is typically measured in foot-pounds, okay? Some airplanes, they do it in percents. They can do percent torque. They say, okay, this is the max torque is 100%, and this is the min torque is 0, right? But you can convert that into a foot-pounds, excuse me, pounds torque. And then K, and K is the conversion factor to take, so you have torque is force times, force over distance times rotations per minute. So you have rotations times force divided by distance per distance minute, something like that, when you do the equations that way. And so K is taking essentially the radius of the, 2 pi gives us the area, of the propeller, divided by 33,000. And so it's a constant of 0.001904. So that gives us the shaft horsepower. So if we want to know how much power is being put out the output shaft, remember there's typically a small amount of jet thrust, and jet thrust is given in pounds, right? And we can't just add pounds to horsepower. So we have to convert that force in pounds, divide it by 2.5 as the conversion factor, and gives us to get us what's equivalent shaft horsepower. And equivalent shaft horsepower is the amount of horsepower that the prop's developing plus the amount of horsepower that jet is the equivalent to. If we were able to extract the additional energy from that jet thrust and put it into the propeller, that would be that extra little bit of horsepower we're getting from jet thrust. Okay? And so equivalent shaft horsepower, which is known as ESHP, is the shaft horsepower plus the exhaust jet thrust divided by 2.5. Okay? And that gives us that gives us equivalent shaft horsepower of the engine, total power, at a given RPM. Okay, so it's going to vary, obviously, based on RPM. Now, one measurement we have here is torque, and you're familiar with torque from small aircraft, right? Some small aircraft torque reading. We'll look at, with propellers, that's our main power setting, our main power output setting, because we can convert it into, it's important to know for horsepower. There's a couple different ways to measure it, but the aircraft, the turbine aircraft, turboprop aircraft, is going to have a torque gauge in it. And it's going to essentially tell you how hard that propeller is being worked. A couple different ways to measure it. One, not simple, but the CT7s that I worked on, which were set up like this free power turbine with the shaft running down the middle, so they had a long shaft in them. They had a position sensor here. They had a position sensor right here. And those two position sensors would actually measure the amount of physical twist in that steel shaft. And the more twist that was occurring, the greater the torque. So at 0 torque, the two sides of the shaft would be passing the sensors at the same time. You put more load on the prop, it would start to lag behind the one at the free power turbine. And it would sense that how long it takes to get, from when the one at the free power turbine passes the torque sensor or the position sensor till the one up at the gearbox passes the position sensor. The bigger that difference, the more twist was being implied on the shaft and the more torque was there. That's one option. Another option, like the King Air, it looks at the oil pressure in the engine, in the core, in this area, compared to the oil pressure in the prop gearbox. And there is that oil pressure difference, they've been able to calculate the amount of torque from that. So that's another way of doing it, is looking at oil pressure in multiple locations and converting that. Any questions?